The National Electrical Code, also known as the NEC, does not specifically mandate an external protection device, also known as an EPD, for uninterruptible power supplies, called UPS. However, certain sections of the NEC could indirectly influence the decision to install an EPD. Section 110.10 states that electrical equipment must be protected from overcurrent in accordance with its rating. Section 445.16c indicates that Class 1 inverters must be protected from fault currents flowing from the output to the input. Section 445.20 specifies that UPS systems must be listed as a single assembly, that is, including all protective devices. The decision to install an EPD for a UPS should be based on several factors. Firstly, consider the UPS design. Some UPS have built-in protection that meets the requirements of the NEC. Secondly, think about the system size. Large UPS systems may require additional external protection to ensure adequate overcurrent protection. Thirdly, understand the code enforcement, as local code requirements may vary and may necessitate an EPD. Fourthly, perform a risk assessment. The potential consequences of a UPS failure should be considered. Fifthly, refer to the manufacturer's recommendations. The UPS manufacturer may recommend an EPD for optimal performance and safety. If an EPD is deemed necessary, the following options may be considered. One option is a circuit breaker, which interrupts the circuit when the current exceeds a predetermined threshold. Another option is a fuse, which melts and breaks the circuit when the current exceeds its rating. A third option is a current limiting device called CLD, which limits the current during a fault condition. If an EPD is installed, it should meet certain installation considerations. It should be connected in series with the UPS input or output. It should be rated for the appropriate current and voltage. It should be properly coordinated with the other protective devices in the system. In conclusion, while the NEC does not explicitly require an external protection device for UPS, other factors may influence the decision to install one. A risk assessment, manufacturer's recommendations, and local code requirements should be considered when determining the need for an EPD. Section 110.3 B of the NEC covers examination, identification, installation, and use of equipment. This section states that listed or labeled equipment shall be installed and used in accordance with any instructions included in the listing or labeling. This means following the manufacturer's instructions for the UPS and any associated protection devices is crucial. Article 408 of the NEC provides requirements for switchboards, switchgear, and panel boards. While it doesn't directly address UPS protection, it sets standards for overcurrent protection and coordination that can be relevant to UPS installations. Proper overcurrent protection is vital for preventing damage to equipment and ensuring safety. Coordination of protective devices, such as circuit breakers and fuses, ensures that only the affected part of the circuit is isolated during a fault, minimizing downtime. Article 700 of the NEC covers emergency systems. If the UPS is part of an emergency system, additional requirements may apply, including specific requirements for overcurrent protection and system coordination to ensure reliable operation during emergencies. Article 701 addresses legally required standby systems. Similar to emergency systems, legally required standby systems may have specific requirements for overcurrent protection and coordination if a UPS is part of the system. Article 702 covers optional standby systems. While these systems are not legally required, the NEC still provides guidelines for their installation, including considerations for overcurrent protection and coordination if a UPS is used. In addition to the NEC, other standards and regulations may apply to UPS installations, depending on the specific application and location. These may include Underwriters Laboratories called UL standards, Institute of Electrical and Electronics Engineers called IEE standards, and local building codes. UL standards provide safety requirements for UPS equipment, including testing and certification procedures. IEE standards offer guidance on various aspects of electrical systems, including protection and coordination. Local building codes may have additional requirements for UPS installations, such as specific requirements for fire protection and ventilation. A thorough risk assessment is essential for determining the appropriate level of protection for a UPS system. This assessment should consider factors such as the criticality of the load being protected, the potential consequences of a UPS failure, and the likelihood of overcurrent or fault conditions. Based on the risk assessment, appropriate protection devices can be selected and coordinated to minimize the risk of damage or downtime. Consulting with a qualified electrical engineer or other expert is recommended when designing and installing UPS systems, especially for large or critical applications. These professionals can help ensure that the system meets all applicable codes and standards and provides the necessary level of protection. Regular inspection and maintenance of UPS systems and associated protection devices are crucial for ensuring their continued reliability and safety. This includes visual inspections, testing of protective devices, and replacement of components as needed. Proper maintenance can help identify and address potential problems before they lead to failures or safety hazards. When selecting an APD for a UPS system, it's important to consider the specific characteristics of the UPS and the load it is protecting. This includes the UPS voltage and current ratings, its fault current capability, and the load sensitivity to voltage disturbances. The EPD should be selected to provide adequate protection without causing nuisance tripping or otherwise disrupting the operation of the UPS or the load. Coordination studies are an important tool for ensuring that protective devices in a system are properly coordinated. These studies involve analyzing the fault current characteristics of the system and selecting protective devices with appropriate time current characteristics to ensure that the device closest to the fault clears the fault first, minimizing the impact on the rest of the system. Surge protection devices, called SPD, can be used to protect UPS systems from voltage surges caused by lightning or other events. SPD should be installed at the input of the UPS to divert surge currents away from the UPS and the load it is protecting. Grounding is an important aspect of UPS system protection. Proper grounding helps to minimize the risk of electrical shock and provides a path for fault currents to flow back to the source, allowing protective devices to operate properly. The NEC and other standards provide detailed requirements for grounding electrical systems. Transient voltage surge suppressors, also known as TVSS, are similar to SPD and can be used to protect UPS systems from voltage surges. TVSS devices are typically installed in parallel with the UPS input and are designed to clamp voltage surges to a safe level. Harmonic filters can be used to reduce harmonic distortion in UPS systems. Harmonic distortion can cause overheating of equipment and other problems. Harmonic filters are typically installed in series with the UPS output and are designed to filter out harmonic currents. Isolation transformers can be used to isolate UPS systems from the electrical grid. Isolation transformers can help to improve the quality of power supplied to the UPS and can also provide protection from ground faults. Monitoring systems can be used to monitor the performance of UPS systems and associated protection devices. These systems can provide alerts when problems are detected, allowing for prompt corrective action. Monitoring systems can help to improve the reliability and availability of UPS systems. Remote monitoring capabilities allow for continuous oversight of the UPS system's health and performance from any location with network access. This feature is particularly valuable for unmanned sites or facilities where on-site personnel may not be readily available. Data logging features within monitoring systems provide a historical record of key parameters such as voltage, current, frequency, and battery status. This data can be analyzed to identify trends, predict potential issues, and optimize system performance over time. Notification systems can be configured to send alerts via email, SMS, or other channels when critical events occur, such as power outages, battery failures, or high-temperature conditions. This enables prompt response to minimize downtime and prevent equipment damage. Integration with building management systems, called BMS, allows for centralized monitoring and control of the UPS system along with other building infrastructure components. This integration streamlines operations and enhances overall facility management capabilities. Load analysis is crucial to determine the appropriate size and configuration of the UPS system. This involves assessing the power requirements of all connected equipment, including their inrush currents and operating characteristics. Oversizing the UPS can lead to unnecessary costs and reduced efficiency, while undersizing can result in system overload and failure. Battery management is an essential aspect of UPS system maintenance. Regular testing and maintenance of batteries are necessary to ensure their reliability and longevity. Factors such as temperature, humidity, and charging cycles can affect battery performance. Battery monitoring systems can provide valuable insights into battery health and help to identify potential issues before they cause problems. Environmental considerations play a role in UPS system design and operation. UPS systems generate heat and require adequate ventilation to prevent overheating. Operating temperature range for the UPS and batteries must be taken into account to ensure reliable performance. Noise levels can also be a concern, especially in office or residential environments. Redundancy configurations can enhance the reliability of UPS systems. Redundant UPS systems provide backup power in case of failure of the primary UPS. Various redundancy configurations are available, such as parallel redundant and hot standby systems. Maintenance bypass switches allow for isolating the UPS from the load for maintenance or repairs without interrupting power to critical equipment. These switches provide a manual means of transferring the load to utility power or another backup source. Automatic transfer switches, called ATS, automatically transfer the load to an alternate power source in the event of a UPS failure or power outage. ATS devices ensure seamless transition to backup power without interruption to critical equipment. Power distribution units, called PDU, provide power distribution and management capabilities for UPS systems. PDU can include features such as circuit breakers, power monitoring, and remote control. Power factor correction, also known as PFC, improves the efficiency of UPS systems by reducing reactive power consumption. PFC can help to lower energy costs and reduce the load on the electrical grid. Energy efficiency is an important consideration in UPS system design and operation. High-efficiency UPS systems can save energy costs and reduce environmental impact. Look for UPS systems that meet recognized energy efficiency standards, such as Energy Star. Scalability is a key feature for UPS systems that need to adapt to changing power requirements. Modular UPS systems allow for adding or removing power modules as needed to match the load demand. This flexibility enables efficient use of resources and reduces the need for oversizing the UPS. Communication interfaces enable UPS systems to communicate with external devices and systems. Common communication interfaces include serial ports, USB ports, and network interfaces. These interfaces allow for remote monitoring, control, and data logging. Cybersecurity is an increasing concern for UPS systems that are connected to networks. Implement appropriate security measures to protect the UPS system from unauthorized access and cyber threats. This includes using strong passwords, enabling encryption, and keeping software up to date. Emergency power off, called EPO, switches provide a means of quickly shutting down the UPS system in case of an emergency. EPO switches should be located in easily accessible locations. Seismic bracing may be required for UPS systems in earthquake-prone areas. Seismic bracing helps to prevent the UPS system from tipping over or being damaged during an earthquake. This ensures that the UPS can continue to provide power to critical equipment during and after a seismic event. Battery runtime calculations are essential to determine the appropriate battery capacity for the UPS system. These calculations take into account the load demand, battery discharge rate, and desired runtime. Proper battery sizing ensures that the UPS can provide power for the required duration during a power outage. Battery disposal should be done in an environmentally responsible manner. Batteries contain hazardous materials that can pollute the environment if not disposed of properly. Follow local regulations and guidelines for battery recycling or disposal. Cold start capability allows the UPS system to start without utility power being present. This feature is useful in situations where the utility power is unavailable, such as after a prolonged power outage. Automatic restart capability allows the UPS system to automatically restart after a power outage. This feature ensures that critical equipment is quickly restored to operation without manual intervention. Input power factor is a measure of how efficiently the UPS system utilizes electrical power. A high input power factor indicates that the UPS system is drawing power efficiently from the utility grid. This reduces energy waste and lowers electricity costs. Output voltage regulation ensures that the UPS system provides a stable and consistent voltage to the connected equipment. This is important for sensitive electronic devices that can be damaged by voltage fluctuations. Output frequency regulation ensures that the UPS system provides a stable and consistent frequency to the connected equipment. This is important for equipment that relies on a specific frequency for proper operation. Transfer time is the time it takes for the UPS system to switch from utility power to battery power during a power outage. A short transfer time is important for preventing interruptions to critical equipment. Audible noise levels should be considered when selecting a UPS system, especially for office or residential environments. Look for UPS systems that have low noise levels to minimize disruption. Agency approvals such as UL, Canadian Standards Association, called CSA, and European Conformity, called CE, indicate that the UPS system has been tested and certified to meet safety standards. Look for UPS systems that have the necessary agency approvals for your application. Altitude dirting may be necessary for UPS systems that are installed at high altitudes. The air is thinner at high altitudes, which can affect the cooling of the UPS system. Consult the manufacturer's specifications for altitude dirting information. Ingress protection, also called IP, ratings indicate the level of protection that the UPS system provides against dust and water. Choose a UPS system with an appropriate IP rating for the environment in which it will be installed. Neutral to ground voltage should be minimized in UPS systems. High neutral to ground voltage can cause problems with sensitive electronic equipment. Proper grounding practices can help to minimize neutral to ground voltage. Harmonics are distortions in the electrical waveform that can cause problems with electrical equipment. UPS systems can generate harmonics, so it is important to choose a UPS system with low harmonic distortion. Isolation transformers can be used to reduce harmonics in UPS systems. The K-factor is a measure of the harmonic content of a load. Loads with high K-factors can cause problems with electrical equipment, so it is important to choose a UPS system that is compatible with the K-factor of the load. The crest factor is the ratio of the peak voltage to the root mean square, called RMS voltage of a waveform. UPS systems should be able to handle the crest factor of the load without distortion. Total harmonic distortion, also known as THD, is a measure of the amount of harmonic distortion in a waveform. UPS systems should have low THD to minimize problems with electrical equipment. Voltage distortion can cause problems with sensitive electronic equipment. UPS systems should provide clean and stable voltage to the connected equipment. Power quality is an important consideration for UPS systems. UPS systems should provide clean and stable power to the connected equipment. Reactive power is the power that is used to create magnetic fields in electrical equipment. UPS systems should be able to handle the reactive power of the load. Apparent power is the product of voltage and current. UPS systems should be sized to handle the apparent power of the load. Real power is the power that is actually used by the load. UPS systems should be sized to handle the real power of the load. Load shedding is the process of disconnecting non-critical loads from the UPS system during a power outage. This can extend the runtime of the UPS system. Generator compatibility is important if the UPS system will be used with a generator. The UPS system should be compatible with the generator's voltage, frequency, and power output. Black start capability allows the UPS system to start without any external power source. This is useful in situations where there is a complete power outage. Wraparound power refers to a situation where power is fed back into the utility grid from the UPS system. This can be a problem if the UPS system is not properly designed. Anti-islanding protection is used to prevent the UPS system from feeding power back into the utility grid during a power outage. This is important for safety reasons. Utility interactive UPS systems are designed to work with the utility grid. These systems can provide power to the grid during peak demand periods. Smart grid compatibility is becoming increasingly important for UPS systems. Smart grid compatible UPS systems can communicate with the grid to optimize energy usage. Demand response is a program that allows utilities to reduce power consumption during peak demand periods. UPS systems can be used to participate in demand response programs. Virtual power plants are networks of distributed energy resources, such as UPS systems, that can be used to provide power to the grid. Microgrids are small-scale power grids that can operate independently of the main utility grid. UPS systems can be used in microgrids to provide backup power. Energy storage systems can be used with UPS systems to provide longer runtime during power outages. These systems can store energy from the grid or from renewable energy sources. Flywheel energy storage systems use a rotating flywheel to store energy. These systems can provide high power output for short periods of time. Battery energy storage systems, called BESS, use batteries to store energy. These systems can provide power for longer periods of time than flywheel systems. Ultracapacitor energy storage systems use ultracapacitors to store energy. These systems can provide very high power output for very short periods of time. Renewable energy integration is becoming increasingly important for UPS systems. UPS systems can be used to integrate renewable energy sources such as solar and wind power into the grid. Solar power can be used to charge the batteries in a UPS system. Wind power can be used to charge the batteries in a UPS system. Fuel cell technology can be used to provide backup power for UPS systems. Fuel cells use hydrogen and oxygen to generate electricity. Combined heat and power, called CHP, systems can be used to provide both electricity and heat for UPS systems. CHP systems are more efficient than separate electricity and heat generation systems. Trigeneration systems can be used to provide electricity, heat, and cooling for UPS systems. Trigeneration systems are even more efficient than CHP systems. Building automation systems, called BAS, can be used to control and monitor UPS systems. BAS systems can optimize energy usage and improve system reliability. Remote monitoring and control of UPS systems is becoming increasingly common. This allows for managing the UPS system from anywhere in the world. Cloud-based monitoring and control systems are becoming increasingly popular. These systems offer many advantages, such as scalability, reliability, and security. Big data analytics can be used to analyze data from UPS systems. This can help to identify trends and improve system performance. Artificial intelligence, also known as AI, can be used to optimize the operation of UPS systems. AI can be used to predict power outages and optimize battery charging. Machine learning, also known as ML, can be used to improve the accuracy of power outage predictions. Predictive maintenance can be used to prevent UPS system failures. Predictive maintenance uses data analysis to identify potential problems before they occur. Augmented reality, also known as AR, can be used to assist with UPS system maintenance. AR can provide technicians with real-time information and guidance. Virtual reality, also known as VR, can be used to train technicians on UPS system maintenance. VR can provide a safe and realistic training environment. Drones can be used to inspect UPS systems. Drones can access hard-to-reach areas and provide high-resolution images. Robotics can be used to automate UPS system maintenance. Robots can perform tasks such as battery replacement and cleaning. 3D printing can be used to create replacement parts for UPS systems. 3D printing can reduce the cost and lead time for replacement parts. Blockchain technology can be used to secure data from UPS systems. Blockchain technology provides a secure and tamper-proof way to store data. The Internet of Things, also known as IoT, is connecting UPS systems to the Internet. This allows for remote monitoring and control of the UPS system. Edge computing is bringing computing closer to the UPS system. This can improve the performance of the UPS system. 5G technology is enabling faster and more reliable communication with UPS systems. 5G technology can improve the performance of remote monitoring and control systems. The cloud is providing a scalable and reliable platform for managing UPS systems. The cloud allows for storing and processing large amounts of data from UPS systems. Data centers are relying on UPS systems to provide backup power. Data centers require highly reliable UPS systems to prevent downtime. Hospitals are relying on UPS systems to provide backup power. Hospitals require highly reliable UPS systems to protect patients. Financial institutions are relying on UPS systems to provide backup power. Financial institutions require highly reliable UPS systems to protect transactions. Manufacturing facilities are relying on UPS systems to provide backup power. Manufacturing facilities require highly reliable UPS systems to prevent production losses. Telecommunications companies are relying on UPS systems to provide backup power. Telecommunications companies require highly reliable UPS systems to maintain communication services. Transportation systems are relying on UPS systems to provide backup power. Transportation systems require highly reliable UPS systems to ensure safety and efficiency. Government agencies are relying on UPS systems to provide backup power. Government agencies require highly reliable UPS systems to maintain essential services. Educational institutions are relying on UPS systems to provide backup power. Educational institutions require highly reliable UPS systems to prevent disruptions to learning. Retail businesses are relying on UPS systems to provide backup power. Retail businesses require highly reliable UPS systems to prevent losses from downtime. Small businesses are relying on UPS systems to provide backup power. Small businesses require affordable and reliable UPS systems to protect their operations. Homeowners are relying on UPS systems to provide backup power. Homeowners require affordable and easy-to-use UPS systems to protect their electronics. The future of UPS systems is bright. UPS systems are becoming more efficient, reliable, and intelligent. UPS systems are playing an increasingly important role in our society. As technology continues to advance, UPS systems will become even more essential.